Okay, let's begin by talking about something new here, something called vector fields. Okay, let's start out this way. Suppose D is a subset of Rn. So I'm thinking of n as being either 2 or 3. So I'm saying D is some subset of the plane or space. Okay, a mapping from D into Rn, it's going to match the same n here generally, is called a vector field. So here, let me be clear about this. D we think of as a point in either the plane or in space, but what it's mapping into we think of as a vector. Okay, so it's going. We think of a vector field this way: attached to each point in the plane or in space of D, there's a vector attached to the end of it. Okay, all right. Let's go to their next slide then. Let's just take some simple examples here. Suppose I'm working with a plane here. F of the point xy is the vector x negative y. This is what? A vector field from the plane xy to two vectors. Okay. Here's another vector field we're calling G here. It takes points in 3 space. Here, Cartesian coordinates x, y, z. And it gives you what? Another 3 vector here, and it's this way: negative 1 over x squared plus y squared plus z squared to the 3 halves times what? The position vector x, y, z. This would be pointing in the opposite direction to the actual position vector here. Okay, this is an important one. This is, in essence, a multiple of this is the gravitational field. Okay, but it's a vector field from space to 3 vectors. Okay, here's some drawings on here. I will be putting this PowerPoint online for you to look at here. They've got some drawings. This is from OpenStax here. The gravitational field exerted by 2 astronomical bodies on a small object here. Okay, you notice the closer you get to the object, the stronger the gravitational field. Here's another kind of common field called a vector field. Imagine some sort of fluid flowing at each particular point in space and possibly in time. You've got what? The fluid has a particular speed, which would be a magnitude, and a particular direction. So that would be a vector, right? We all know that velocity is a vector here. So anyway, all right, here's a visual representation of the radial vector field. F of xy is x over 2I plus y over 2j. Now, if you think about this, emanating from the origin, the position vector from the origin to the point xy would be what? xi plus yj, if you're going to use I and j like they're doing here. Again, this is OpenStax here. You can see what you've really done is what? You've taken half the position vector, okay, at each point in space. Now, those will be attached to what? Each particular point in the plane here. So you see where I'm pointing here? Now, when I'm really close to the origin then, I have what? Really stubby, really short position vectors, okay? As I move further away out here, as I move further from the origin, of course, the position vector is longer, and half the position vector is longer. So these are getting longer the further away I get away from the origin. Notice their direction is what we call radial. It means they're radiating strictly right away from the origin. They're pointing away from the origin, aren't they? Here's another radial vector field with overlaid circles. So this is the exact same field, overlaid circles here. So these circles are what? Points where they have a constant distance from the origin. Can you see that these guys, these vectors are always going to be orthogonal to these lines of constant magnitude, or curves of constant magnitude, circles centered at the origin? Okay? All right. Let's look at another one here. A visual representation of this field, y comma negative x. Notice that this field is sort of swirling. It's swirling around the origin. Okay? It's actually, each little point here, I want you to think about this. You can, as a hint, just think about the dot product here. At each little point here, it's actually orthogonal to the position vector of the point right here, okay? It's actually orthogonal to the position vector of the point. Notice these are getting longer or larger in magnitude as we get further away from the origin. Just think about the magnitude of the vector y comma negative x, and that will make sense, right? Okay. Let's take a look at another one. Again, this is going to be important for things like gravitation. You see this kind of phenomenon here. As a practical matter, sometimes it's going to be difficult to actually draw these vector fields for the following reason. Let's come in here and think of this one. This is actually the previous one, except for we've done what? We've divided by the scalar x squared plus y squared on both of the components. Now, if you think about it here, as you're getting closer to the origin, actually the vectors are getting what? Longer. They have larger magnitude as we get towards the origin here. So if you imagine, see these points here getting close to the origin, the vector is actually having a larger magnitude. It's getting longer. The further I get away from here, okay, the smaller the actual magnitude of the vectors, okay? All right, so this type of behavior happens with things, you know, certain fields and stuff, electromagnetic fields and stuff, where, you know, and the same thing even with gravitational fields. You see when you get really close to the gravitating body, the vector that representing the gravitational force might go, you know, be really long, okay? And these actually drawn vectors can interfere with each other. So there's some limitation on our drawings here as far as clarity goes here. But there it is, okay? Here's another one, a visual representation of this vector field. Notice that the I and j components are fixed. They're always equal to 1, but the j component is actually whatever the z value is, okay? So along the xy plane, you just have what? You would have these fixed vectors 1, 1, 0, or I plus j, if you want to think of it that way. It'd be the same at every point on the xy plane. But here, if you go off the xy plane, they'd be pointing what? Downwards as you get values of z below the xy plane. Those would be negative, wouldn't they? So it would be pointing down. But above the xy plane, you've got positive z values, so the vectors are pointing up away from the xy plane in that case. But anyways, this is an example of this happening here. Okay? Okay, this is an example where I was talking about the gravitational field, okay? F is pointing the opposite direction to the position vector x, y, z, okay? It's negative g m1, m2, right? This is the force of gravity, okay? Divided by r cubed. Think about this. The magnitude of this vector is actually 1 over r squared, where r is the magnitude of the position vector x, y, z, right? So you're really getting the inverse square law here, okay? Negative sign because it's what? Pointing towards the origin in this case. Okay? Alrighty. Let's take a look at one last one here. They call this a gradient field, okay? Gradient of f, remember that what that was? That's the partial derivative of f with respect to xi plus the partial derivative of f with respect to yj, okay? Here I've got what? A scalar function at each point. F of xy is x squared, y squared. So think about what the actual gradient of f would be as a vector field at each point here. And this is actually what it ends up looking like. Okay, I will turn you on to some software that allows you to actually draw some of these vector fields. Okay, now the gradient of f here, when you've got a gradient field, this is also known as a conservative field. These types of fields are going to be very important in the work in the rest of the chapter, okay? Now, we won't always have things that are gradient fields. See, the idea is not every vector field is actually induced by a gradient. There doesn't necessarily exist for a general field a scalar function f such that the gradient of f actually induces that particular field. But when we do have that situation, we say that we've got a gradient vector field, or we shall see later why we use this term conservative field. Okay? Well, that should be okay for a general introduction as to what a field is. You guys can think about a vector field, electromagnetic field, well, actually the electric field, and then what? Gravitational fields, What's another type of vector field? Velocity field. Okay, those would be common examples of something like this going on. Okay, alrighty? All right, it should be okay for an introduction here.